person who's walking near tall buildings. Sometimes tall buildings make like a canyon, and the wind has to get through somewhere. Depending on how much space those buildings take up, wind can be really windy when you turn a corner around a building. And that happened to this person. So when they turned a corner, the wind stopped them. If the wind did 100 joules of work to stop them, what had been their velocity before the wind stopped them? We can assume that if the wind did 100 joules of work to stop them, then that means that that person had 100 joules of kinetic energy before they stopped. So I'm going to plug in that 100 joules in for KE, assuming all that work used to be kinetic energy. It said it's a 50 kilogram person, and we're looking for their velocity. Half of 50 is 25, and now we're trying to find out their velocity, so I'll make that 25 cancel and get v squared, and then I'll make that squared cancel and get v. So now I know where I'm going. Let's see. To make that 25 cancel, it says v squared times 25, so I'll divide both sides by 25. Now it's just v squared on this side, and 100 divided by 25 is 4. That's v squared. We still need to get it to v, so the opposite of squared is square root. Square root of v squared is v. Square root of 4 is 2. There we go. And it's velocity, so it's in meters per second. They were going 2 meters per second. So we're doing the Doppler effect today. I have a short video that if y'all want to watch, if you want to watch this Big Bang Theory video, it's on the Google form. There's a link, but you don't have to watch it. I'm going to show it, and then I'll talk about it a little bit. I was unable to play this video, I think, because of the camera's plugged in, but it worked for the other videos. Anyway, you can see Sheldon's dressed as the Doppler effect here. I hope you all got to watch it at home. He's got where am I? He's got stripes that are real close to each other here, and stripes that are kind of far away here. This is what happens with the Doppler effect. What he describes it as is, he says it's a change in frequency caused by relative motion between the source of a wave and an observer. He says he can talk better than I can. Change in frequency caused by relative motion between the source of a wave and its observer. What that means is if there's a car driving by and it's honking its horn, there's relative motion between you and the car. If you're just standing there and the car drives by, there's relative motion. You're stopped, the car is moving. So if it honks its horn, on its way to you, those waves get compressed, and that increases the frequency of the wave, and you hear a higher pitch. And then it goes by you, and those waves get stretched out, and so it goes. Have y'all heard that, the Doppler effect in real life? I like physics because we already know this stuff. We're just like figuring out exactly what's happening or why it happens and such. Anyway, when those waves get compressed, those are areas of compression. When they get stretched out, we learn a new word. Those are areas of rarefaction. Have you all heard that? Rarefaction? I had heard it, but I had forgotten. Anyway, rarefaction. Let me show you something else here. Where's my fire truck? Well, the internet. I guess I don't know if I really need the fire truck. There's the fire truck. So this is from y'all's assignment that we're going to do. This "wee-oo" that it says is kind of misleading because it implies that the siren is going and that you're hearing the "wee" part of the siren here and you're hearing the "ew" part. But it does that all the time. It doesn't do that because of the Doppler effect. It just goes "wee-oo, wee-oo, wee-oo." So imagine that this fire truck's honking its horn, and what's happening is this person's listening. There's relative motion between this observer and this wave source. And when this fire truck's going toward this person, then this person, these waves get compressed, and this person hears a higher pitch. So it's as though it were honking its horn instead of having its siren, because the siren thing is misleading, which we use. So as they leave, the waves get stretched out. Areas of compression, areas of rarefaction. And because they're stretched out, this person hears a lower frequency. It's kind of neat. And I'm saying the word observer, not listener, on purpose. This happens with somebody who is watching as well as somebody who is listening. In astronomy, this is used a lot. So if you get if you're watching a faraway star in your telescope and you're an astronomer, are y'all doing this already? Listen, please. If that star is coming towards you, the waves of light that are coming towards you get compressed, and they're now a shorter wavelength, and that changes the color of the wave. Remember I said Roy G. Biv goes from low energy to high energy, and after you get violet, you get ultraviolet, and that's why you can get a sunburn, or after that, depending on who you are, after that you get X-rays, and that's why those are bad for you, or they can see through your skin or whatever, because they got higher energy. Anyway, shorter wavelength waves have higher energy too. So Roy G. Biv goes from long wavelength to short wavelength. So you may have heard these terms before. I know. If something is moving towards you and those waves get compressed to get a shorter wavelength, if it's a source of visible light that's coming towards you that you're looking at in your telescope, those waves get a little more blue because the wavelength gets compressed, the wavelength gets shorter. So astronomers call that blue shift. If it's moving away from you, it gets red shift. If it's moving away really fast or towards you really fast, if it's moving away, it might redshift all the way to radio waves out of the visible spectrum. So you have to look at it with a different telescope. Or if it's moving towards you really fast, you might have to look at it with an X-ray telescope. Kind of neat. X-ray telescopes are really cool to use, like these sideways mirrors, because you point X-rays right at a regular mirror, it goes right through it. You have to do the mirror almost sideways, and then you've got a bunch of series of mirrors that guide those X-rays to a sensor. It's kind of neat. Anyway, yeah, Doppler effect isn't just with sound; it's with light too. We can actually do math. Those astronomers definitely have to do math if they want to figure out exactly how fast those things are moving. That's what they're all about, is quantifying what is going on in the universe. There we go. So here's an example that I did that's doing math. So I gave you two ways to do math on some of these questions. Half of them are conceptual about the Doppler effect, and half of them are doing math. So one way is you can follow these steps. First, figure out how much relative motion there is relative to the speed of sound. And you get a number that way. And then, if you're going toward it, you add 1. If you're going away from it, you say 1 minus that number. And then the third step is multiply the original frequency by that new number you got after you added or subtracted. Or you can do it with the formula down here, where F is the new frequency that you're going to hear because of the Doppler effect. F naught, in A-U-G-H-T, that's what this little circle is. I like to think of it as original frequency, even though it's not an O, it's a naught. That little circle is called a naught. So that's the original frequency, like what you would hear if there were no relative motion between you and the wave source. Like if you're in the car honking the horn, what you would hear. And here's your relative velocity, whatever relative motion there is, what that velocity comes out to be, and the speed of sound. In this assignment, I use different speeds of sound because depending on how dense the air is, you can get slightly different speeds of sound. And the different speeds of sound I use may not be exactly accurate, but the speed of sound does change, and that's what I was trying to communicate. Anyway, let's work this number 8 out. That's the example I used to do this one and to plug that in here, but let me show you what I did. So it's asking, what's the frequency heard by a driver going 15 meters per second toward a stationary train horn? So 15 meters per second is their relative velocity, 15 meters per second toward. We'll need to keep that in mind when we're doing these things up there. The stationary train horn has a frequency of 800 hertz. That's the original frequency that we'll use. And the speed of sound is 340.6. So with my steps, I figured out the ratio of the relative velocity versus the speed of sound. I got 0.044. So if we're doing a percent, that could be 4.4%. So and we're not going to use a percent in our calculations. That's confusing, so don't worry about that. But this is how much that frequency is going to increase or decrease. It'll increase by 4.4% or it'll decrease by 4.4%, depending on if we're moving toward or away. If that relative motion is toward or away, the wave source. Since ours is toward, we'll say 1 plus 0.044, and that way, when we get our frequency, we'll say 800 hertz, our original frequency, times 1.044. That way it's a little more than 800. And so it turns out it'll be 835. If we were away from the sign, if the relative motion was away from the observer, then we'd say 1 minus 0.044 and end up with, instead of 1.044, it'd be 0.956 or something. And then we'd say 800 times 0.956, and it'd be slightly less than 800. Because it's moving away from us, the sound would get lower. That's why our frequency would be lower. And that's basically what I did over here. I got the same thing, 835. Now, this question that I asked you, what would be the train horn's frequency as heard by the driver if the driver were also stationary? There's no relative motion between the driver and the wave source, so this is kind of a trick question. So, well, it's easy to overthink anyway. I'm not trying to trick you with it. But because there's no relative motion, that means that that train horn frequency wouldn't change. It would be its original frequency, 800 hertz. Please try out this Doppler effect assignment. You guys got questions about it? Oh, okay.